And welcome, calculus folks. This is going to be a bit of a weird back and forth lesson. You're watching this, and hopefully you've tried the warm-up. I'm about to take that up momentarily. In this lesson, there's a small investigation, and there's a handout that should be posted on the website in PDF version that you're going to fill out. And it's about 15 minutes worth of work. And I think it would be best if you did that at home. You could save it for class, except for then you're only getting this small video done, and then you won't see any of the take-up videos or the examples until class. So I would say you'd want to do that in all the videos and then save this for class. Everything before here, maybe you're doing tonight. But that is up to you. So the warm-up, we're asked, first of all, to find s prime at t. That's easy, because this is an easy function. We have s at t is this. Doesn't need to be changed form. This is just the sum of two functions. We take the derivative and just take the derivative of the two pieces. That's great. Find the slope of s at t equals 2. Well, the slope of s is this function, right? This is the slope function. So all I'd have to do then is find s prime at 2, which is 3 times 2 squared plus 4, which is, let me check my notes here, bada bing, bada boom on the calculator, 16. This is a weird question. Find the slope of s prime at t. So we want to find the slope of that. Well, that's no problem. That's just, if s prime at t is this equation, what we want to do is take the derivative of it, right? And I'm going to mix my notations here a little bit just for a second. So I'm going to take the derivative of it with respect to t, right? Just taking the derivative of some function, taking the derivative of the left and right side. The derivative of this is no problem. This is another easy function to take the derivative of. This is just 6t. The 4 disappears. And then notice, what is this? This is the derivative of the derivative, right? The derivative of the derivative. Here's the special new notation. It's the second derivative. Second derivative. It's the slope of the slope function. And at at t equals 2, rather, I just solve that. That's 12. And we're going to be talking about what these things might mean. We saw earlier that often s represents the distance. We don't use d in calculus class because it gets mixed up with the Leibniz notation. And here we go. Hopefully you've got the note printed off, either the full copy or the skeleton copy here. Higher order derivatives. Higher order derivatives is this idea of derivatives of derivatives. And that's going to lead to motion analysis, which is, you've done some of this in physics class if you've taken physics. But this is probably the most natural application of the derivative that there is. In fact, I think this is what Newton was all about, thinking all about when he invented the calculus. So expectations are there. It says, if y equals f at x, then y double prime is equal to f double prime at x. We can read that as double prime is the second derivative of f with respect to x. And as it says here, y double prime is the rate of change of the rate of change. You follow that. We have some function f that's doing something, and we take the derivative. Remember, it was the rate of change of that. Well, if I take the rate of change of that, it's the rate of change of the rate of change, or the derivative of the derivative. Leibniz notation, good old Leibniz. I said, well, where y is a function of x, we think of this as y prime, right? This is dy by dx, or the change in y with respect to x. And the second derivative then is the change of the derivative with respect to x. And the way Leibniz sort of simplifies that is this double dy over d of x squared. And this doesn't, these aren't exponents here. This is kind of the number of times we've taken the derivative, the second derivative. So if, what would it be if it was the seventh derivative? Why would we take the seventh derivative? Just for funsies. Okay, the seventh derivative of y with respect to x would look like that. And this means not exponents, but we've taken the derivative 7 times. Okay, great. Onward and upward. It says, we will see that the second derivative will give us some special meaning when we are graphing functions in Chapter 4. But it has immediate meaning if we consider a position function of an object moving in a straight line. And that's the, taking the derivative of the derivative is no big whoop, but this idea of if my, s at t is the position of an object, if that's the position of object, well then what's s prime at t? Well, it's the rate of change of the position. That's the velocity, right? That's the velocity, i.e., if I wanted the velocity function, I take the derivative of the position function. And you notice we call it position just because it's sometimes in a straight line, because sometimes we're talking about left, right, sometimes we're talking about east, west, sometimes we're talking up, down, north, south, that sort of thing. So the position, we don't really care about that. Then notice the derivative of this, the derivative of the derivative, the rate of change of the velocity, the rate of change of the velocity, the change in velocity is whether you're speeding up or slowing down, the acceleration. Yes, I can hear you physics students groan. If you haven't taken physics, don't worry about it. This is just, we're familiar with, the position or distance that an object is away. We're certainly familiar with velocity and acceleration, this idea of speeding up or slowing down. Acceleration is the rate of change of the velocity or the second derivative of the position function. Okay. The next, that's it for this first part of the video, but I'm going to introduce this this activity. So this activity is on a piece of paper that looks like this, and your idea, you're going to fill it out. Don't worry about the notes, and don't worry about this number line looks like it's out of place, but that goes with my notes. So your task is to fill this in and fill this in for each of the functions. First the position function, then the velocity function, and then the acceleration function, and then there's a little conclusion at the end. And your job is to put that, don't worry about the notes for now. Notice that it says you could use the TI-83, which I know you're not holding one, but remember from functions that we could download this, and this appears on my website somewhere. If you wanted to, you can also, if you want to download that, you could also use Desmos. So remember Desmos, Desmos.com. And this is probably what you'll be using. I don't know. And then I'm going to put in my function. What's funny about Desmos is you can just put in the right hand side. Well, no, it won't let me put in a t. I have to put in an x. X to the exponent. Well, I've forgotten the function already. What was the function? X to the exponent 3 minus 13x squared plus 40t. Not t, x, sorry. And then you're going to want to change the settings, and of course you're good at this already, but we want the y values to go from maybe negative 30-ish is what it was on the thing, to positive 50-ish, maybe 50, not 507, but 50. Step by, well, that's not bad. Dandy. And then if I want the values for the table, I can sort of just click on them, right, until I get the right value. Where's 1? Well, 1's down there somewhere. Certainly, you could just put them into your calculator, right? Absolutely, you could. Okay, there's 128. Um, there's 236 that happens to be at a maximum, and so on. You can fill out the table very quickly using Desmos. And notice the first derivative, easy peasy, 26x plus 40, and then you can fill in the sheet very quickly. Okay, I'm stopping there. You're gonna go fill in the sheet really quickly, and then come back for part two.